Hi everyone, and welcome back to our aqueous geochemistry course or water quality course, depending where you are. Today's module or today's video is on intro to dissolved gases because we're starting a new module on dissolved gases. I think this is a really interesting and important subject area for lots of people, whether you're a fisheries scientist, an ecosystem scientist, or a geochemist. So for this module, our learning objectives are to understand and apply Henry's law and Van Hoff equations to relevant environmental gases, to apply these ideas to understand controls on dissolved gas concentrations in rivers and lakes, and have a general understanding of different gases' exchange rates and environmental consequences of these rates. So to get us started, I sort of wanted to share a research study that my grad student Natalie Schmer has been leading. And this study is in the city of Fort Collins, so this is just a map of Fort Collins. And at the top left of Fort Collins, if you're not familiar with the city, up here at this site that we call Risk Canyon Road, that's where the Cache la Poudre River comes out of the sort of high elevation mountains, relatively clean water, unimpacted by sort of agriculture or urban settings. And so this is sort of a site that is the water is sort of unimpacted by the city so far. And we set up a bunch of sensors going down the Poudre River, catching more and more essentially agricultural and urban runoff. And this whole study was motivated by something relevant to dissolved gases. So the city of Fort Collins and I, in 2018, we discussed installing the sensor network because there had been a fish kill. So down here, sort of by the purple archery range and environmental learning center dots, there was an event where like hundreds of fish died and washed up on shore, and no one was really sure why. And sometimes when you have fish kills in sort of urban rivers like this, it can be because the dissolved oxygen went to such a low level in the river that there was sort of no oxygen left for the fish to survive, and so that can be one driver. So we installed all these sensors that measure dissolved oxygen in the stream and a bunch of other things, and that this study is still ongoing, and we're sort of using this data right now to investigate it. We haven't seen that same hypoxic event since we've installed the sensors, but I expect we will see it eventually. And just to sort of familiarize yourself with some general controls on dissolved oxygen. So now the map has been flipped and it's on the left just for reference. In this video that you'll see, what happens is we're tracking a parcel of water as it goes down down the river. And so we're going to pick up the water parcel first at the top of the canyon, and then we're going to sort of go down. And what we're measuring is water depth, the salinity of the water, so basically specific conductivity here. And then we're also measuring the dissolved oxygen concentration as a percent of saturation. And I'll just go ahead and play this video now, and we'll sort of see the dynamics of dissolved oxygen. So you can kind of keep your eyes on that. And we're going to pick up different sites that respond differently. So as we go down the river, we pick up different sites, basically at the rate that sort of water flows. And so now we can see all sites, and what we see is this diurnal in the dissolved oxygen trend, we see this clear diurnal pattern where and I'll just pause it there to talk about that a little bit. So if you look at these diel or diurnal curves, what that's showing is basically during the day when it's sunny out, algae that are in the river are producing oxygen. So they're doing photosynthesis and they produce oxygen in the water column, and that super saturates the water with oxygen. So there's a lot of water, or there's a lot of oxygen in the water sort of at this time. And then as you sort of go into nighttime, a lot of those algae are then consumed, and so oxygen is consumed as part of respiration, and that lowers the oxygen level below 100% and down to something like maybe 60. So that's sort of this is a clear biotic signal when we see this kind of thing. That's often how we think of it, at least. And so now I'll just play the video again. And so we see this diurnal signal again, but then it gets cut off at this random part here. So the algae were starting to go gangbusters again. They were growing, and then they got cut off. And if you look up at the depth curves, at each site, the algae production got cut off right when the depth went up. And so if you live in the city of Fort Collins, you know we installed a whitewater park. And so this was basically them releasing a wave for that whitewater park. And it had a big effect on both the salinity of the system, so it really dropped the salinity because the water came from Horsetooth Reservoir, has a lower salinity than the basin, and it also had a huge effect on dissolved oxygen, where basically it kicked out all the algae and they stopped doing their thing, and so then you had a much more muted diurnal curve. And so this is sort of like one way we can. These are the kinds of data we will look at for this section, and what we want to understand is like what are the controls on how much oxygen is dissolving in water. Why are some of these sites different? So why do some sites have lots of oxygen during the day, or really big diel curves, and other ones have really relatively flat diel curves? And so that's sort of like the general context. And I think you can build some intuitions about the controls on these by just looking at an actual video of what at these sites. So we're going to zoom in on Risk Canyon up here, and Natalie has put out these really cool. If I could advance the slide. Yeah, Natalie has put up these really cool time-lapse photography, and so we're just going to watch snowmelt from May of 2020 to basically mid-June of 2020. And when we're watching this, I'm just going to sort of talk about what are the controls on dissolved oxygen. So dissolved oxygen at this site, remember that was the green graph, and if you remember that had one of the lower diel curves, and it didn't really have a lot of like variation, and that's because this site is relatively steep. So at flood level, which is the snow melt, so it's really high water, you can still see that there's a lot of white water going around. And when you see white water, that means that there's turbulent exchange of gas with the environment. And so you have a really reactive environment. So even if there's algae there producing a lot of oxygen, that oxygen isn't stuck in the water. It's rapidly exchanged with the air. And so it's sort of released out. And you can see this, again, at even low flow. If we replay the video, at low flow, there's still a lot of like white water turbulent exchange at this site. And of course, as you get to higher and higher flows, you have even more turbulent exchange sort of going on throughout the image. And so this is not at the same time period that the previous video was in October, but this just gives you a sense of sort of like how variable gas exchange can be at a single site in the Poudre River, where snowmelt is the dominant hydrologic driver. So another thing that's really exciting about sort of working on dissolved gases right now is there's some really cool progress being made by people that I've worked with and that all of us have worked with. So Alison Appling there in the top left wrote a paper in 2018 that was basically a new method for calculating what is the sort of, let's say, turbulent exchange of dissolved oxygen with the environment versus what is the biotic production. And what that allows you to do, if we get a little pointer and highlight this GPP here, what that allows you to do is it actually allows you to calculate gross primary production of the river. And that's a sort of ecosystem measure that allows you to really characterize the river. Is algae a really big part of this river's ecosystem, or is all of the energy coming from external sources like leaf fall? And Alison developed this method in a way that is way less field intensive than previously had been used, because to understand the difference between biotic production versus turbulent exchange with the environment has been a really hard problem. But we've improved upon it. Not we, Alison has improved upon it a lot in the recent past. And so there's some really cool work going on in this field. And what Alison's work allows us to do, this is another colleague, Phil Savoy. He wrote a paper recently that sort of took Alison's data set that she built and normalized the gross primary production to sort of get at a question about, like, as my previous advisor would say, do rivers have rhythm? So what is the rhythm of primary production in rivers? And so basically he found that there's sort of there's sort of two different types, or four different types depending on how you cut it, but there's like spring peak productivity places, so that's like over here, and then there's summer peak productivity places like over here. And these vary, but basically there's canonical shapes of primary production. And again, this is all because we understand how dissolved oxygen is produced in these ecosystems, and how it is in sort of held in the river even after turbulent exchange. So Phil's work is really interesting, and it allows us to sort of look at over 200 rivers as sort of whole ecosystem experiments, and we get to sort of describe what's going on in the ecosystem because we have a good understanding of the dissolved gas controls. And then finally, I just want to talk about another colleague. I went to grad school with Joanna Blaschak, and this is just a really interesting paper. And if you're a fisheries biologist or something, this is sort of really important, and this is relevant to the fish kill in the Poudre River that we started with. So what Joanna found in Durham, North Carolina, where we did our PhDs, was basically that these rivers had basically long periods of hypoxia or low oxygen levels, and that even when they recovered, if there was a tiny little storm that would push out water from upstream, like sort of impoundments, that would then cause another anoxic event. So you can see that there's this little storm here, and then there's another anoxic event, and then there's a little storm here, and then another anoxic event. And so basically this river was pounded by either really high flows that sort of scoured the bed and took out the algae, essentially, because you'll see that the dissolved oxygen concentration never goes above 100%. Or they were sort of little floods that pushed out a bunch of dissolved oxygen. And so if you're a fish in this pond, that's sort of where this sensor was, you're not having a good time because you're frequently in this really low oxygen level. So yeah, this is sort of an intro to motivate why we want to understand Henry's Law and turbulent gas exchange and all the things we're going to talk about in future lectures, but I hope it got you motivated and excited to learn more about that. And this is just the last bit to say, like, algae production, so dissolved gas concentration, is basically the major driver of fish kill. This is a fish kill in China. So understanding dissolved gas concentration and controls is critical for understanding stream and lake ecosystems, fisheries, water quality, and more. And that's it. Here's the citations, and I will see you next time.